Welcome, ladies and gentlemen, to our guide for how to solve physics problems. This guide is going to show you a focused, organized way to solve physics problems, and you will be required to solve problems using this structure on your test. So let me repeat that. You'll be required to use this method to solve problems on your test. This method allows me to see your process when I grade your tests, and in physics, the process is as important as the answer. This is true both for physics and for your grade. You cannot receive full credit without showing your process, without showing your work. And in particular, you have to show it in this way that I'm going to show you. The reason that I make you solve problems in this way is because this approach will organize your answer and will make it easy for me to read, and in addition, it will make it easy for you to solve the problem. Oftentimes, the most difficult part of a problem is figuring out where to start and trying to get going on the problem. And once you get going, you can kind of solve it from there. Solving problems with this process takes care of that for you. You know where to start. I'm telling you what to do to start. And you have steps to go through that will solve the problem every time. So it's really important that you pay attention to this method and you use it for solving your homework problems. If you use this method to solve your homework problems, that practice will mean that you don't have to think about doing the method when the test comes around. It will just be automatic for you, and it'll just be the way that you solve physics problems. In the case that your answer is incorrect, your process and the work you show will be the source of partial credit for incorrect answers. In the case of correct answers, the process will show that you solve the problem in the right way and that you understand the physics of the problem. So when we solve physics problems, we use a systematic approach. This approach is an organized and focused approach that helps us think about the problem in a useful way. We don't use a scattershot approach where we start writing down random equations until one of them seems to have the right stuff in it, and we don't just fling stuff at the wall to see what sticks. This approach is the same approach that we use to solve any problem, but in the case of physics problems, it's particularly useful because they may be a little more difficult to solve and require a little more thought than just an average everyday problem. So the approach has steps. The first step is to summarize the problem. So we like to summarize the things we know, what the problem looks like, and what it's asking of us. We have to know what we're actually trying to answer. So that's an important part of summarizing the problem. Imagine I need to attach a wooden sign to a wooden post. The problem is to make the sign stick to the post permanently. That summarizes the problem. Next, we identify the correct tool for the problem. In this class, that means identifying physical principles and equations that are appropriate to the problem and that help us find what we want to know. In our example with the wooden sign and the wooden post, we might decide to use a hammer and nails to solve that problem, the problem of making the sign stick to the post permanently. The next step is we apply the tool, or in physics, we do the math. For this class, applying the tool is just turning the crank on the mathematics to express the desired variable in terms of the known variables. In our example with the wooden sign and the wooden post, we just hammer the nails through the sign and into the post to make the sign stick to the post. And then finally we check our answer. In this class, that means we do a unit check and a sanity check, and we'll talk more about what those are later. And in our example with the sign and the post, we might look in and see that the nails went into the post properly. We might tug on the sign a little bit to make sure it's securely attached to the post. And then we've checked our work, and we're sure that it's worked properly. So let's talk about the approach by modeling it on an example problem. Our example problem is this one. Mary is going to drop off a cliff into the ocean 15 meters below. How fast will Mary be going when she hits the water? So our first step, we summarize the problem. And we start by drawing a picture. So here's Mary on top of a cliff with the ocean below. In particular, we draw a useful picture, a picture that helps us solve the problem. My picture here doesn't have much aesthetic value, it looks pretty crappy, but it is useful for solving the problem because it allows me to visualize what the problem looks like and to draw on it to write in quantities that I know and what I'm going to want to know. So, first step, we've drawn a picture, and we've drawn a useful picture in terms of physics. The next step, we choose a coordinate system. So remember that I keep stressing that you get to choose your coordinate systems, and you should choose them advantageously. Now, I could pick something like, say, this, and that coordinate system is perfectly fine. However, it's a pain in the ass to use, so we don't really like it that much. So I'm going to pick a coordinate system that's useful to the problem. And in particular, this problem we're going to solve with one-dimensional kinematics. Conveniently, because that's the only tool we've developed so far in the class. So, I'm going to pick the origin to be at the height of Mary's feet, and I'm going to pick the positive x-hat direction to be down. So why did I choose down? Well, I know in this problem, everything's going to be happening in that direction. All the motion is going to be in that direction, so I choose x-hat so that everything is positive. I could choose x-hat to be up instead, but then everything that happens in this problem is going to be in the negative x-hat direction, and I'm going to have to add minus signs all throughout it, and that just sounds like a pain to me. In general, physicists are nothing if not lazy. So I'm going to make the problem as easy as possible, and I want x-hat to be down, because that's the direction everything's going to move, and then all of my stuff, all my variables that we're about to list are going to be positive. So I choose a coordinate system, and in particular, I choose a coordinate system that makes the problem easy for me. Next, I list the variables that we know. So we know that from here, the top of the cliff to the water, we'll say XF, X final, her final position at the water, is 15 meters below. So that's the first variable we know. XF equals 15 meters. Okay? Because of the way I've chosen my coordinate system, I also know that x initial equals 0, because I specifically picked my coordinate system to make that the case. We know that Mary's going to start from rest. She's not moving at the beginning, so v initial equals 0. And then finally, we know that Mary in this problem is just going to be affected by the acceleration due to gravity, so a equals little g equals 9.8 meters per second squared. Now we've listed the variables that we know. Finally, we state what we're trying to find. In helping students solve homework problems in the past, I've often asked them, so what are you trying to find in this problem? And the answer is, I don't know. So this is actually a really important step. I can't solve the problem if I don't know what I'm trying to find. So the last thing I'm going to do in the setup of the problem here is make sure that I know what we're trying to find. In this case, it asked us, what is Mary's speed when she hits the water? So her speed at XF, the point where she hits the water, or V final equals what? That's what we're trying to find. So at this point, we've done all the work for the first step. We've summarized the problem. The next step in our problem-solving approach is to select the correct tool for the problem. This means thinking about the physical principles that we know and the equations associated with those principles and selecting the one that's appropriate to this problem, the one that helps us find what we've identified that we want to know. In this case, we have an object that's pretty heavy, a person, falling a relatively short distance, a 15-meter cliff. So kinematics with constant acceleration is the appropriate tool for solving this problem. So I identify the appropriate physics tool, 1D kinematics. And then I write down the equations that are appropriate to this problem in their general form. So the two kinematics equations that I want to use for this problem are x equals x naught plus v naught t plus 1/2 at squared, okay, the kinematic equation in its general form, and v equals v naught plus at. Then we've finished this second piece of the problem solving tool. We've identified the correct tool for the problem. Next, we apply the tool, or in a physics class, that means we do the math. Note that this says we do the math and not do the arithmetic. This means we do not put numbers in right now. Our first step in solving a physics problem is not to plug in the numbers. Again, do not put the numbers in right now. We wait until we have the final answer to plug in the numbers, and so we do the math with the variables. We can make simplifications appropriate to our problem as we solve the math. What does this mean for this problem? In general, it means the one number that we can put in is 0. So recall that the two kinematic equations that I want to use are these two. And then let's make them appropriate to this problem. I chose my coordinate system such that x naught would equal 0, and Mary starts from rest, so v naught equals 0. So those two terms go away, and this equation appropriate to this problem becomes xf, x final, equals 1/2 g t squared, because the acceleration we said was going to be little g. We know that xf is 15 meters, but we're not putting in numbers right now. This second equation, to make it appropriate to this problem, we remember that again, Mary starts from rest, so v naught is 0, and v final equals gt. Now remember that what we wanted to find in this problem was v final. Well, v final equals gt. I know little g, but I don't know t. So I'm going to manipulate the first equation, xf equals 1/2 gt, to solve for t. So if I do that, I get t equals 2xf over g in a root. Now I can take that and put it into this equation, and I will have v final in terms of variables that I know. So v final equals gt equals g 2x final over g in a root. If I bring the g inside the square root, I have 2xf g squared over g in a root, and that's equal to 2xf fg in a root. So then my answer is vf equals 2x final g all under a root. Note that I keep an organized approach to this. I have steps that I just go through. And note that each equation that I wrote was always true. I never wrote something or manipulated an equation in such a way that I made one equal sign no longer true. All of my equal signs are true all the way through all of my math. it's very important that I do this so that somebody else can read my math later, and so that I can keep track of everything that's going on. And if my answer is not correct, when I go back to look at it, I can find the mistake. So this answer, VF equals 2xfg in a root, this is what I call the real answer. This is the answer that shows how the thing we want to know depends upon the things that we already know. Remember that we already know xf and g, 15 meters and 9.8 meters per second squared. And what we wanted to know was VF, the speed that Mary is moving when she hits the water. This answer expresses VF in terms of things we know, so this is the answer that shows how the thing we want to know depends on the things that we already know. This is the answer that explains the physics of this problem. The next step in our problem-solving approach is to check our answer. So remember, our answer was VF equals 2xfg, all under a root. And we do two checks on this. The first check is that we do a unit check. So remember that an equal sign tells us that two quantities are the same, and for physical quantities to be the same, they must have the same units. So when we do a unit check, we just plug in units for all of the variables in the problem. We know that velocities are meters per second. And then on the other side, we have no units on the 2. That's just a number. We have a distance, that's a meter. And then we have an acceleration, which is meters per second squared. And all that stuff is in a root. This is equal to meters squared over seconds squared, all in a root, which is meters per second. So you can see on the left side and the right side, our units work out to be the same. This is a good indication that our answer is correct. If the units don't work, we know that the answer couldn't possibly be correct. And if they do work, there's at least a decent chance that our answer is correct. The next thing we do is a sanity check. And a sanity check, we check the behavior of our equation with the behavior of things in the physical world. So we make sure that our equation makes physical sense if we think about how our answer depends on the variables that we know. So what does that look like? Well, we can think about the way things work in the physical world, and we can say, what if XF was larger? What if Mary jumped off a taller cliff? Well, she should be going faster when she hits the water than she was going if she jumped off a shorter cliff. So if XF increases, VF should increase. And you can see that in our equation, if we do raise XF, VF will increase. So for sanity, we say VF increases as XF increases, and this checks out. The other thing we can say is that if gravity was stronger, if gravity was giving a bigger acceleration and the distance of the cliff would stayed the same, Mary should also be going faster when she hits the water. She'd have a bigger acceleration, she would cover the same distance, so she should be going faster at the end of that distance. And again, in our equation, you can see if we make g bigger, VF gets bigger. So VF increases as g increases. And again, that checks out. That makes sense with the physics involved in this problem. So if we were solving some random problem, like our signpost example, this would be the end. This is the end of the problem-solving approach. For a physics problem, there is one more little afterthought step that we do. And that is now we can finally plug in the numbers, okay? Now that we've done all the other stuff, we've done the unit check, we've done the sanity check, we got the answer in terms of the thing we want to know in terms of the variables that we already know. Now in this final step, we can plug in the numbers. So this is 2 times 15 meters times 9.8 meters per second squared. All that stuff in a root. That's equal to 17.146 meters per second. And this 15 meters was presented to us as 15.0 meters in the problem. So we have 3 significant figures, which means that our final answer is 17.1 meters per second. So there's our final numerical answer. V final is 17.1 meters per second. And with this one, we can do a quick mental check that our answer makes sense just kind of at the order of magnitude level. So in the case of velocity, if you're from the United States, you might have a better intuition in miles per hour. And you can get the ballpark of miles per hour by multiplying the meters per second by 2.2. So if we do that, we get around 38 miles per hour. If you're from somewhere other than the United States, you probably have a better intuition for kilometers per hour. And we can get kilometers per hour from meters per second by multiplying by 3.6. This one doesn't give a ballpark. This is an exact conversion. So Mary is going 61.6 kilometers per hour. And what I say when I say we can make an order of magnitude guess is if we think about 38 miles per hour, an order of magnitude lower would be, say, 3 miles an hour. That's about the speed you can walk. And we know that if Mary jumped off a 50-foot tall cliff, she should be going faster than you could walk when she hits the water. So that's good. We're an order of magnitude bigger than that. An order of magnitude bigger might be 300 miles per hour. That's faster than you can drive any car. And we know if Mary jumped off just a 50-foot cliff, she shouldn't be going faster than you could drive any car. Imagine driving a car at 300 miles per hour into a wall. That would be like her hitting the water at 300 miles an hour. We know that that's not the case. We know she can jump off of a cliff that's about 50 feet and she can survive. So our order of magnitude makes sense. An order of magnitude smaller, that's way too slow. We can definitely feel that. An order of magnitude bigger, that's way too fast. We can definitely be sure of that. So order of magnitude, this answer looks about right. So we did a unit check, it worked. Our sanity checks all made sense. And our order of magnitude of our answer, that makes sense too. So chances are we have the right answer here. So note also that by waiting until the very end to plug in the numbers, we were able to easily check that our answer made sense. We could do a unit check and a sanity check. If we were plugging in numbers in the first step, we would just have all these numbers that don't really mean much to us. They wouldn't actually be describing to us how our final answer depends on the things that we know. They wouldn't be describing the physics of this to us. We can also look at our answer to learn interesting physical properties about the problem or problems like it. So in this case, it's very interesting that Mary's velocity when she hits the water, it doesn't depend on the distance in a directly proportional way. It depends on the root of the distance. So if she were to fall twice as far, so if VF equals 2 XFG, and then we make XF go to 2XF, or if she were to fall twice as far, we would get root 2XF 2G. And the difference between... So that was incorrect. It goes to VF equals 2XF 2G. And that's equal to root 2 times 2XFG in a root. So our answer, if we double the distance that Mary falls here, her speed increases by root 2. It doesn't double. It increases by the root of 2. So we've learned an interesting physical property of this system by looking at our answer while it's still written in variables. If we plug in the numbers early, we can't do things like this. So this is another reason that we don't plug in the numbers on the first step. Also, if there was a follow-up question that was meant to be quick, we don't have to solve the whole problem again. If we put in the numbers at the beginning, if someone asks a follow-up question, for example, what if someone asks, what if the cliff was twice as tall? Well, I've already solved that right here in one line. If the cliff is twice as tall, we would take this answer and multiply it by root 2. But if I plugged in the numbers at the beginning, I would have to do the entire problem again because I wouldn't be able to tell what exactly happened to my distance, okay? So by doing it with the variables like this, I can answer follow-up questions more quickly unless they're changing something significant about the problem. Another example of a follow-up question that's even a little more involved is, what if Mary was jumping from the same height but into a pool on a space station on the moon, where the acceleration due to gravity is 1/6 what it is on Earth? Well, if that was the case, chances are I'd have to do the problem entirely again, unless I have an answer in this form right here. Then I can say, oh, G goes to 1/6 G, and I can just plug that into the answer that I already have, and I can answer that follow-up question again in one line, just like I did down here. So this method of solving the problem has real advantages if there are any kind of tag questions on the end of problems as well. So let's look at the whole process. This is how you should be solving this problem and what you would have to write to receive full credit for solving the problem in this class, okay? We have the process in black, our steps in the process, and in red over here we have what you have to write down to receive full credit for the problem. It looks like a lot, but it doesn't actually take a long time, okay? We can still solve the problem quickly while writing all of these things. So, we read the problem. Mary is going to drop off a cliff into the ocean 15 meters below. How fast will Mary be going when she hits the water? And then we go ahead and solve the problem. First, we draw a picture. She's falling into the water. Okay. Then we choose a coordinate system. I choose it at her feet with the x-hat direction going down. Then we list the known variables. XF here is 15 meters. XI equals 0. VI equals 0 because she's at rest. And A equals G equals 9.8 meters per second squared. And then we state what we're trying to find. I want to know what V final is. V final equals what? How fast? Okay. Summarize the problem is done. Then we identify the correct tool. This is 1D kinematics. And I write down the appropriate equations for this problem in their general form. So the two equations I'm going to use are x equals x naught plus v naught t plus 1/2 at squared, and v equals v naught plus at. There we go. The equations in their general form. Then I do the math. I turn the crank. Remember that x naught and v naught are 0, so these first two terms of the first equation fall out, and I have x final equals 1/2 g t squared. I have v final again, V naught falls out, equals GT. I have V final here. I know G, I don't know T, so I solve the first equation for T. So therefore, T equals 2xf over G in a root. I plug that in for T in this equation down here, and I get G and then 2x final over G in a root. I bring the G inside the square root, and I have G squared 2xf over G. All of that in a root. And then I simplify, and I get 2xf G in a root. So VF equals 2xfg all in a root. And this is, remember, what I call the real answer. So the do the math part is done, and I've just shown my work to turn the crank on the mathematics. I do units. Meters per second equal meters times meters per second squared all in a root. That's meters per second, so units check out. I do sanity. For sanity, VF increases as XF increases, and that makes sense. That checks out. I'm running out of space in this little half page, so let's go up here. VF increases as G increases, and that checks out. So I've done my unit check and my sanity check, and then finally I plug in the numbers, and I get VF equals 2 times 15 meters times 9.8 meters per second squared. So VF equals 17.1 meters per second. And that's it. Now we're done with the problem. I ran out of space a little bit here because I'm trying to solve it on half a page and write big enough that you guys can see it. But you can see it doesn't take that long to solve a problem in this way once I'm used to solving it with this method. So we'll solve every problem for this class in this manner. You'll see that I use the same approach when I solve problems in front of you in class, and you should use it on your homework problem as well. Again, use it on your homework problems. You'll want to get comfortable with the method because you are required to use the method to get full credit on a test problem. If you practice the method on your homework problems, it will become a tool for solving problems in an organized, efficient way, rather than a hindrance. After a handful of problems, you'll feel like you've solved problems correctly when you do it this way because you'll have done checks on it. You can be confident in your answer. And on the test, it'll help you be efficient with your time, allow you to be confident in your answers there as well, and help you get partial credit on something if your answer doesn't come out correctly.